So today let's take a look at some power factor meters. Let's see how do they work, what's inside, and if I manage to, I will also power them and show them in operation, and I will measure the power factor of some appliances or loads. And in one of my previous videos I was talking about wattmeters, and these are kind of related to this, so you might want to watch this video as well. These power factor meters are basically measuring the power factor of an AC load or appliance based on the phase shift between the current and the voltage. I was already explaining it in the previous video in more detail. A resistive load draws just real power because its current is in phase with the voltage, but there are also reactive loads, which draw a reactive power. They can be inductive or capacitive. In an inductive load, the current is lagging after the voltage. If it's purely inductive, it's lagging 90 degrees. If it's partially inductive, it's lagging less than 90 degrees. And in a capacitive load, the current is leading ahead of the voltage. If it's purely capacitive, it's ahead by 90 degrees. If it's just partially capacitive, it's less than 90 degrees. If it's partially capacitive, it's somewhere between capacitive and resistive, and if it's partially inductive, it's somewhere between inductive and resistive. And of course, a unity power factor load doesn't have to be just a resistor. It can be anything where the current is in phase with the voltage. It can be, for example, a power supply with a good power factor correction, or a properly corrected inductive load, which has the right amount of compensation, using the right capacitance of a compensation capacitor. For example, a well-compensated motor, or inductive fluorescent fixture, or discharge lamp fixture, or a capacitive load with the right compensation inductor. But anyway, these power factor meters are measuring the power factor based on how much the current is shifted in reference to the voltage and which way. And they are usually used to determine the right amount of compensation for a load. If the load is inductive, it can be compensated using a capacitor, and if it's capacitive, it can be compensated using an inductor. Because of course, to use the power lines efficiently, the power factor should be as close as possible to 1. The lower the power factor, the more current it draws without actually doing any useful work. Reactive loads load the power lines or wiring or generator without doing anything useful. They are just exchanging power with the power plant or generator. The power goes one way and then the other way, and it alternates. But they can compensate each other. Inductive can compensate capacitive, and capacitive can compensate inductive. Because as you can see, the current goes the opposite way. An inductive current and a capacitive current are rotated 180 degrees. So for example, an inductive load can be compensated using a capacitor, and then it doesn't have to pull the reactive power through the long power lines and exchange it with the power plant. Instead of it, it's just exchanging it with the capacitor, which is much closer to it, and so it doesn't cause an unnecessary load on the power lines. But now let's finally get to the power factor meters, and let's see how do they measure the power factor. They basically measure the phase shift of the current in reference to the voltage, and the system inside of them is actually even more complex than the system in wattmeters. In the previous video I was showing the system of a voltmeter and a wattmeter. A voltmeter has just one coil, a moving coil or a rotating coil inside of a magnetic field of a permanent magnet. If it's a voltmeter, the coil is connected to the measured voltage, usually via a resistor, and the deflection of the needle depends on the voltage. A wattmeter has a similar system. It has a voltage coil which is turning in a magnetic field again, but instead of a permanent magnet, it has a coil, a current sensing coil. And a power factor meter goes one step further, and it actually has 3 coils. It has 2 moving coils and 1 stationary coil, or 2 stationary coils and 1 moving coil. Now let's take a look at this power factor meter. It goes from 0.5 power factor capacitive through 1 all the way to 0.5 inductive power factor. And the marking says 1.5% accuracy, vertical operation, and the system is balanced ferrodynamic. It's for 3 phases, but only one line is thick, which means that only one phase is actually sensed. It's only sensing the current in one phase, and it assumes the other 2 phases are loaded the same way, and it's tested for 2 kilovolts. And I guess the power factor meter has a similar system to the wattmeter, but it has one extra coil. It still has the current sensing coil, but instead of one voltage coil, it has two voltage coils moving in the magnetic field, and each of them is at a different angle. And each of the voltage coils is connected to an AC voltage with a different phase. Usually one of them is connected to a voltage which is ahead of the voltage of the phase you're sensing, and one of them has a voltage on it which is behind the voltage of the phase you're sensing. So basically one of them has a capacitive current in it and one of them an inductive current. And these two coils are basically turning in the magnetic field created by this current sensing coil. And this magnetic field is going through it this way. And in one of these coils the current is ahead, and in one of them the current is behind. Now if the load draws a current which is behind, this current sensing coil gets a current which is behind the voltage, and out of these two reference coils, the one where the current is behind will align with the magnetic field. Let's say the red one has the current behind the voltage and it aligns with this magnetic field which is also behind, and this of course indicates that it's an inductive load. If it's a capacitive load, the current is ahead here, and so the coil with the current ahead will align with this. The magnetic field goes like this, it goes through the coil which is ahead, and so it indicates a capacitive load. The black reference coil also has a current in it which is ahead. And if it's a resistive load with no phase shift, then one of the coils is ahead, one is behind, so they will balance and it will indicate a power factor of 1. Now both coils balance each other. So this is a simple explanation of how it works. And of course you could flip it and have one rotating coil and two stationary coils. Each of them is split into two halves. And this one is rotating in the magnetic field of these, but also these. And it again aligns with the coils where the current has the same phase. And if one is behind, one is ahead, then it balances somewhere in between. But this version is a bit problematic because this is a current coil which usually has a high current in it, and making a moving connection with a high current is a bit tricky. The moving coils in these systems are usually connected using very thin springs and they can't carry a high current. So it's probably easier to make two moving connections to two coils, but with a very low current in them. But this thing is very similar, you just flip the stationary and moving part of it. And the coil again aligns based on the phase of the current. This is the current sensing coil and these are the reference coils. One gets a current which is behind the voltage and one gets a current which is ahead of the voltage. And this is true at least for this one which is symmetrical both into capacitive and inductive. It might be a bit different for this one, which only goes to inductive, 0 inductive to 1, and doesn't go to capacitive. In this one maybe one of the coils gets an inductive current which is behind the voltage, and the other one might actually get a resistive current which is in phase with the voltage. But now let's start exploring the internals. Let's begin with this one. The system is again ferrodynamic, 3 phases but current sensing in one phase, 2.5% accuracy, vertical operation, 2 kV test voltage. The current sensing coil is rated for 5 amps and 380 volts for the voltage coils or reference coils. And it has this housing with some mounting bits which are coming off, and this back cover with terminals, probably 2 for the current sensing coil and 3 for the voltage coils. One is common, and there is a schematic on it. These 3 thick lines are the phases, and this arrow indicates that here is the supply and here is the load, and in this case it's sending the current using a current transformer, which basically steps down the current. This was probably used in a substation where it was sensing a current much higher than 5 amps, so it was using a current sensing transformer where the primary has less turns or just 1 turn and the secondary more turns. And of course transformers transform the voltage in the same ratio as the number of turns, but the current is transformed in the opposite ratio. So having more turns on the secondary steps the current down. And this current sensing transformer was probably chosen in such a way that the secondary current is never more than 5 amps. And here is the current sensing coil in the system and 2 voltage coils or reference coils, and the common terminal goes to the phase where the current is sensed, and the other 2 terminals of the voltage coils go to the other 2 phases via resistors. And in the other 2 phases it's not sensing the current, it's just using these phases as a phase reference, basically to get AC voltages with different phases. And the phase of the current in the current sensing circuit is compared with the phase of these 2 phases, and one of these reference phases is ahead of this phase and one of them is behind this phase. This thing is basically sensing current in one phase but using the other 2 phases to generate a phase shift simply without having to use capacitors and inductors. But I guess it could be modified for a single phase operation. And this one measures from 0.4 capacitive all the way to 0.4 inductive with 1 in the middle. But now let's try to see the internals. The back cover seems to be on 4 screws, so let's unscrew it. I removed 4 screws and the cover partially comes off but not fully, and I can see some power resistors in it, a lot of them. The back cover is hanging on wires, I can't remove it completely, and there are 2 boards and each of them has 3 power resistors on it. And they seem to be identical, I guess. And each board basically has 3 resistors that are in series, working as just 1 power resistor. And these are the resistors in the schematic. Each of them is made of actual 3 resistors in a series. And these are basically dropping the voltage from 380 volts between 2 phases to a much lower voltage for the coil. And so this compartment is the power resistors and the rest of it is here. Can I pull it out somehow? And this cover comes off. And here is the system. And here it is. It's basically this current sensing coil, which seems to be made of 2 sections, but they are just in a series. Here's the connection and the 2 wires going to the current sensing coil from the back. And here are the voltage coils. Basically 2 coils at a different angle with some connection springs or wires, turning in the magnetic field of the current coil. And this system is turning the needle. There is 1 connection here, probably the common terminal of the 2 coils, and the other 2 connections here via thin springs or strings or whatever it is. And the angle between the coils is like close to 90 degrees, but not exactly 90 degrees. It's almost like 60 degrees here and 120 degrees here. And of course there is an iron core made of iron layers, bringing the magnetic field of the current coil to these voltage coils. So the system is called ferrodynamic, not just electrodynamic. And it's a balanced system because there is a coil interacting with not just 1 other coil but 2 coils. And there is a little bit of iron glued to the core. This was probably done for fine calibration. So that's it, and now of course everybody wants to see this in operation. So of course I will try to power it, and I also wanted to mention that unlike a voltmeter, current meter or even a wattmeter, the needle in power factor meters doesn't have any directional force. There is virtually no force trying to return it into a certain position. So without power basically the needle stays where you put it or where it left. It doesn't go back. Maybe it moves very slowly, but there is no defined position where it parks with no current. So if there is no load or not enough load, it just shows a random reading, or it just indicates the last state. So it probably has to be used together with a current meter to verify that there is enough load for this to indicate. And to power this I basically need 3 phases, but it's sensing in 1 phase only, which means that it could measure single phase loads, but it still requires the other 2 phases for reference. it could be probably modified to a single phase, but I'd have to replace these resistors with some combinations of resistors, inductors and capacitors, and it would definitely require quite a lot of experimentation to get it right, because I'd have to adjust multiple variables at the same time. I'd have to get right the current in each coil, but also the phase shift of each coil. And of course now the question is, how do I get 3 phases in an apartment with no 3-phase socket? Well, I have just single-phase sockets, but different sockets in my apartment are on different phases. So I will use one phase from this room and I will bring the other phases from single-phase sockets in other rooms, which are on different phases. But before powering this, let's reassemble it. And it seems that each phase is sensed using 3 resistors in a series, and it's 16 plus 16 plus 10 kilo ohms. So it's in total 42 kilo ohms. 42 kilo ohms. And the voltage coil itself is about 2 kilo ohms. So in total 44 kilo ohms for this phase, 44 for this one. And the current coil is of course negligible resistance, 0.1 ohm. And of course I have to stress this is not the right way of obtaining a 3-phase voltage. This is the dodgy one. So that's my power factor measuring system, and let's test it. Let's try to load it using a 40-watt lamp, which is a purely resistive load, and it does show something. It's getting close to 1, but not exactly there. Now let's try 100 watts, and it's getting closer to 1, and 200 watts, even closer to 1, so it seems to work, but it requires enough load to be accurate. It's more inaccurate when the load is too low. Unfortunately, this one doesn't go to 0 capacitive or 0 inductive, so I can't test it using just a capacitor or just an inductor. But let's try to put a fluorescent inductor in a parallel to the lamp. Now it should be partially resistive, partially inductive. So let's power it. And it seems to indicate capacitive. Well, this probably means that my phase order is reversed. The phases are in the wrong order. Let's reverse this phase with this one. The two ones which go to the resistors. Now the phases are reversed and it's actually showing inductive now, so it's right. Now the phases are in the right order. Before this, the one that was meant to be behind was ahead, and the one that was meant to be ahead was behind. Of course, in reference to the phase where I'm connecting this lamp and where it's sensing the current. And without the inductor, it's still going to indicate very close to 1, which is right. But again, with just a 40-watt lamp, it doesn't seem to be loaded enough. With a 200-watt one, it works much better. And now a capacitor, of course. And it's on the capacitive side. And with just the inductor and no tungsten lamp, it goes over a range into inductive. And the inductor in series with the lamp instead of parallel. It reduces the brightness of the lamp, and the power factor is partially resistive, partially inductive. So it's still on the inductive side of the scale. And now, of course, a fluorescent fixture cannot be missing. And it indicates on the inductive side, and it draws over 300 milliamps. And if I stick a parallel capacitor to it, the power factor goes closer to 1. But not entirely so. For full compensation, this actually requires even more capacitance. But you can see that with the capacitor, it actually draws significantly less current. Without the capacitor about 300 milliamps, with the capacitor about 170 milliamps. Oh, 2.2 micro, and one more. And now it's slightly overcompensated, and it goes a bit into capacitive. This is 4.4 micro, 2.2 micro, no compensation. Now I found a combination of capacitors which brings it to a unity power factor. 2.2 micro plus 1 micro plus 0.68 micro. So that's the power factor meter in operation and how it can be used to find the right compensation to minimize the current draw of an inductive or capacitive load. The fluorescent fixture with no compensation is drawing over 300 milliamps, and with the right compensation just 110 or 120 milliamps. Of course, some fluorescent fixtures have a built-in compensation capacitor, but some of them have none. And they might have just a tiny capacitor, but this one is just for interference suppression. Such a tiny one is not for the compensation. For a power factor compensation, it needs much more capacitance than this. This tiny interference suppression capacitor is just 0.047 micro, but for the right compensation it needs about 3 or 4 micro, way more. And that's the marking of the inductor in the fluorescent fixture. And this one says vertical operation, but it might be more accurate in horizontal position. Now it's very close to 1, even with just a 40 watt lamp. And in vertical position it has much more tendency to go down with no current. When it's horizontal, the reading is virtually the same for a 200 watt lamp and for a 40 watt lamp. The system might be out of balance a little bit, but it was probably better when it was new. For the accuracy, it seems definitely better when there is no force trying to bring it back to a particular position. The less force bringing it back, the less current necessary for it to indicate right. So the system in power factor meters is completely different than the system in voltmeters, current meters or wattmeters. In a voltmeter, current meter or wattmeter, there is a magnetic torque generated and this magnetic torque goes against the spring trying to bring it back. So it basically measures the magnetic torque. The more magnetic torque, the more deflection. But in a power factor meter there is ideally no returning force. Ideally it's just floating on perfect bearings and it's just aligning to a certain angle based on the phase angle of the voltage in the coils. In a voltmeter, current meter or a wattmeter, the connections to the coils are actually working as springs with a defined force. But in a power factor meters, the connections are not meant to work as a spring. They are meant to be as easy to move as possible. But now let's finally take a look at these guys. And they seem to be very similar other than they have a different range. And here is the back of them, and this one actually seems to have the original seal on the screw here, so it was never opened. So I'm going to open this one and take a look inside. I don't want to break the seal on this one. But these ones are probably going to be harder to power because this label says it works with a separate ballast or set of resistors or whatever circuitry. It basically requires some external circuitry. Unlike this one, it doesn't have the resistors built into it. The same applies to this one, and there is some code of a schematic C5 and C7. It probably refers to some schematic of how it should be wired, but I really don't know where to find it. But before trying to power it, let's see the internals. This one has 4 screws, this is the one with no seal, and then it should come out, and that's it. And here's the system and the screws falling out. And there is a knob on the cover, but it doesn't go anywhere. It's there probably just because it uses the same housing as some other types of meters. Normally this knob is used to set the needle to 0 with no current, but power factor meters don't have any return position, so this knob is not needed. And now let's take a look at the system. And it seems to be the other version, with 2 pairs of coils, basically 2 coils, but each of them split in half on this iron core, which is stationary, and there is 1 rotating coil in the middle. I can probably remove this cover to see it better. And here is the needle. There seems to be some dampening magnet, creating a magnetic friction with this aluminum plate, so the needle doesn't oscillate. And some counterweight is here. And now you hopefully can see something. 2 stationary coils, each split in half, and the rotating coil inside of it. In this one, the operation is basically flipped the other way. The 2 voltage coils are stationary and the current coil is rotating. There's the rotating coil in the middle. Now you can probably see it. There's the shaft with the needle, some counterweights, the two strings connecting it to the coil. But these are not meant to be too springy. Here's the aluminum plate with the dampening magnet and the rotating coil in the center, and these four coils, which are basically two coils each split in half. And this opposing pair is one coil and this opposing pair is one coil. Basically these are in series and these are in series. And of course there is this transformer, and it's a current transformer. Of course the connecting strings have to be very thin to be very easy to bend, so they can't carry a too high current to the moving coil. So to sense a higher current, there is basically a current transformer with a thick primary and a thin secondary with way more turns probably. And this steps the current down from probably 5 amps to maybe 100 milliamps or less for the rotating coil. This one is basically the one on this picture, and the previous one was on this picture. That's basically it. Now can I somehow power it? It says 5 amps for the current sensing, but I don't know how the voltage coils are meant to be connected. And the coils have some marking. It looks like 2300 turns, 0.1 millimeter diameter. And all four have the same probably. 2300 0.1 millimeter wire. And this is a 3-phase version, not a single-phase version. So I guess the coils were not connected via inductors or capacitors, but just resistors. In the previous one, there was 380 volts connected to 44 kilo ohms or 44,000 ohms, and this is about 8.6 milliamps. The voltage divided by the resistance is the current. So this one was using about 8.6 milliamps for the voltage coils. Not sure how much current this one is using. I have no idea what the external resistors were meant to be for the coils. But the wire is 0.1 millimeter, so I can roughly calculate how much current such a wire can carry at most. Is this 0.1 millimeter? Probably yes. And of course the wire cross-section is pi times the diameter squared, 0.1 millimeters squared, and divided by 4. So the cross-section of the wire is this amount of square millimeters. And a conservative recommendation of a current density in a copper wire is about 2.5 amps per square millimeter. And a wire with this cross-section at this current density can carry about this amount of amps, and this is in milliamps, 19.6 milliamps. And to pass this current through the wire at 380 volts, the total resistance has to be this, about 19,000 ohms or 19 kilo ohms. This is the total of the coil plus the resistor in series. But of course I can use a higher resistance. This calculation gives me the lowest safe resistance, not to overload the wire. So it seems this one requires a bit more current than the previous one. The previous one was using 8.6 milliamps. Let's try to measure the resistances of the coils. Well, this is probably the primary of the current sensing transformer, which is a very low resistance. And here should be the voltage coils, 840 ohms, 840 ohms roughly again for the other coils, and this is just showing them in a series. So the resistance of the voltage coils is lower here, which would also suggest a higher current necessary. But of course the current could be lower. Maybe they were using a lower current density in the wire. But in old school devices, almost every winding had the cross-section of the wire calculated for 2.5 amps per square millimeter. Which is still kind of conservative. Nowadays a lot of transformers or inductors are using a higher current density for cost savings. When you put a higher current density into the calculation, a thinner wire comes out. And of course before powering the coils, let's do a sanity check. Let's calculate how much power the coils are going to dissipate at this current. A resistive power dissipation based on the current going through it is the power equals the resistance times the current squared. And the resistance of the coil is 840 ohms, and this is the current squared, and this gives 0.322 watts. And this probably isn't too much for coils of this size, and this power dissipation is for each pair. So each individual coil is actually getting 0.16 watts, because they are in pairs in a series. I guess this thing can dissipate 0.16 watts. In this one the voltage coils are 2000 ohms and they have this current in them, so each of them is dissipating this power, 0.147 watts. This is very similar to the dissipation of one coil in this one. So this dissipation definitely should be safe, especially given that this one has much smaller coils and still almost the same dissipation. Here the power dissipation is spreading from a much bigger coils. So this is the lowest safe resistance I can use, but now let's try to calculate what's the power dissipation of the resistance at a certain voltage. And of course everybody's screaming that the new nominal voltage between phases is 400 volts, not 380, and the power dissipation of this resistance at this voltage is going to be 8.25 watts. So it definitely needs some power resistors, and also resistors capable of handling this voltage. But to be safe, I will use a bit higher resistance, and then the current is going to be a bit lower through the coils. We have, for example, 6.8 kilo ohms 2 watt resistors. Let's put several in series for each coil. These are 6.8 kilo ohms. I'm putting 4 resistors in series, so the resistance is 4 times higher. Also the power dissipation of resistors in series or parallel of the same values just multiplies by the number of resistors. So the total power dissipation of the resistors can be up to 8 watts. With the same resistances, the power dissipation divides evenly. It doesn't apply to different resistances connected in series or parallel. And the current is going to be 14.7 milliamps. And the power dissipation of the group of resistors is going to be 5.8 watts, which is less than this. And of course I'm neglecting the resistance of the coils, but it's much smaller. With the resistance of the coils added, the current and the power dissipation is going to be a little bit lower. So I have 2 chains of 4 series resistors, 6.8 kilo ohms each, and this is giving in total about 27 kilo ohms each. So here is the dodgy wiring. The phase where I am connecting the load goes to the common terminal of both voltage coils and also to the current coil. And the other terminal of the current coil goes through the load to neutral. And then the terminals of the voltage coils go to the other 2 phases via resistors. These are the other 2 phases. And let's power it with a 40 watt lamp. And it should indicate 1 on this scale. Well, it's trying to go there, but it stops. Maybe a 40 watt lamp is not enough. Let's try a 200 watt lamp. It's getting closer to 1, but still not there. Now connecting the inductor instead of the lamp. And it actually goes to the inductive side, but it probably should go closer to 0 inductive than this. It's definitely moving in the right direction, but not enough. Let's try a much bigger inductor. A 1 kilowatt heater, probably drawing a bit over 4 amps. It definitely goes to resistive, to 1, but still not enough. And of course the motor is negligible compared to the heater in it. This one is going the right direction, but not all the way. But making it operate is quite tricky, not knowing the original way it was meant to be wired. Maybe the wiring is different than this one, because this one is symmetrical with one in the middle and this one not. Let's quickly try this one. This one is symmetrical. Here's the symmetrical one, and with the lamp it's getting kind of close to 1. An inductor makes it go to the inductive side. And the capacitor makes it go to the capacitive side. So it seems to somewhat work, and the scale is quite stretched near 1. This is 0.9, 0.95, so this is probably something like 0.98. That's not too far from 1. I could probably fine adjust it by giving one voltage coil a little bit more current than the other. It's slightly moving to 1. Or maybe the current in the voltage coils is just all too low. But I don't want to risk using much more current, not knowing what it originally was meant to be. So that's the power factor meters. This one seems to work well. This one also works. It probably just needs a little adjustment or a little bit more current, or balance the current between the coils a bit better. But the non-symmetrical one probably needs to be wired a different way. If anybody has the schematic for it, let me know. This one seems to refer to a wiring schematic C7. Well, maybe now I got it. Now it's getting much closer to 1 for the lamp, and much closer to 0 for the inductor. Now it definitely looks much better. Instead of connecting the voltage coils this way, the center point to the last phase, I connected the center point to the neutral. In this one, the center point goes to the last phase, the one that's sensed, where the current sensing is, but maybe this one has to have the center point connected to neutral. This of course changes the angles of the currents, and it also lowers the dissipation of the resistors while supplying the same current into the coils. Because here it's dropping the voltage from about 400 volts and here from just 230 volts. So that's 3-phase power factor meters, and there are also single-phase ones, where the phase shift has to be done using an inductor or capacitor. Here's the current coil and the voltage coils. One is connected via a resistor with no phase shift and one via an inductor. It could also be a capacitor. The disadvantage is that it's frequency dependent. The frequency dependence can be cancelled out by having 3 voltage coils, one connected via a resistor and 2 coils connected one via an inductor and one via a capacitor. And of course this one is 90 degrees in reference to these ones. 3 moving coils, voltage coils in the magnetic field of one current sensing coil. And of course these two are polarized such a way that the magnetic field is adding, not cancelling out. And then of course the magnetic field of this pair of coils in total doesn't change so steeply with the frequency. Because at a higher frequency the capacitor passes more current and the inductor less current, and at a lower frequency the inductor passes more current and the capacitor less current. With just a capacitor the current goes up with the frequency, with just an inductor the current goes down with the frequency. But the total is nearly flat near the nominal frequency. You're operating it somewhere here. So that's a single phase power factor meter which is less skewed by the frequency variation. And the 3-phase ones are not skewed by the frequency variation simply because they are using just resistive droppers, no inductors or capacitors in series with the coils. But I have to stress that these machines are measuring the power factor based on the phase shift between the current and the voltage. These basically work for linear loads, which don't distort the sine wave, they just shift it. So the current sine wave is ahead or behind the voltage sine wave. They don't measure the power factor of harmonically distorting loads, for example rectifiers in switching power supplies or other devices. One of the most common loads with a harmonically distorted current is a rectifier with smoothing. The rectifier passes a current and recharges the capacitor only when the voltage is near its peak here and in the negative half cycle here. This distorts the current quite a lot but causes virtually no phase shift. So such a load can have a low power factor, yet these are going to show a power factor near 1. And of course this current distortion also causes a lot of unnecessary load on the wiring and power lines and the power plant generator. But a low power factor based on a harmonic distortion is a bit harder to compensate than the low power factor caused by a phase shift. A harmonically distorted current cannot be solved by just adding a capacitor or inductor in parallel, and the power factor of switching power supplies or other loads with a rectifier at the input can be partially improved using a passive power factor correction, in the simplest form using just an inductor in series, but this only improves the power factor partially, not fully. It never brings it back to 1. To get the power factor of a rectifier close to 1, you need an active power factor correction, which involves a switching circuitry. But anyway, this video is getting bloody long, and if you're still watching, please consider supporting my channel on Patreon. This really helps me a lot. And big thanks to all of you who already support me. And I might also do some experiments with a synchroscope. And I also plan a video about this component tester or transistor tester.